When considering a body in motion, it is imperative that we understand specific ideas that arise. These ideas include speed, velocity, and acceleration, which work symbiotically with each other to define a body's motion. Speed is simply a result of the distance a body moves and the time it takes to move that distance. In fact, these three concepts are so interconnected that we can create a DST triangle to define each concept. Distance is the product of speed and time. Time is distance over speed, and speed is distance over time. If distance is measured in meters and time in seconds, speed is measured in meters per second. For example, if a car moves 90 meters in 3 seconds, its average speed is 30 meters per second. Now notice that we use the word average to define the car's speed. This means that this is the exact speed at each time interval, as bodies do not move at only one speed. There are many forces and variables that cause a body to slow down or speed up, such as friction, brakes, and resistance. Therefore, in most calculations, we will be asked to calculate average speed. If you wanted to find the actual speed of a body, you would need to discover how far the car moves in the shortest time you can measure. Velocity, on the other hand, is exactly the same as speed, but instead, it has an element of direction, as it is a vector quantity. Therefore, velocity is the speed of an object and the direction in which it travels. For example, a cyclist might have a velocity of 10 meters per second due east. On paper, this velocity would look like this using arrows. Similarly, we could also use negative and positive signs to illustrate the direction of bodies. For example, a velocity of plus 7 meters per second may mean an easterly direction, while a velocity of negative 7 meters per second will indicate a westerly direction. This will ultimately depend on what direction you choose your positive sign to be. Since velocity and speed have the same magnitude, they will share both the same formula and the same units. Finally, acceleration is a concept that defines how a body moves through time under velocity. As a body moves faster through time, it will increase speed, which in turn increases velocity. Therefore, by doing so, the body is seen to accelerate or increase speed constantly. If the body decides to slow down, it will decrease velocity and therefore decrease acceleration or decelerate. Therefore, in simpler terms, acceleration is the rate at which a body changes its velocity. This can be written in this form. Once again, average acceleration is not the same as actual acceleration. Also, it is important to note that a change in velocity is simply the difference between a body's initial velocity and its final velocity. For example, if a car increases its velocity from 0 to 12 meters per second in 4 seconds, the average acceleration is 12 minus 0 over 4, which is 3 meters per second squared. Now, when we are studying motion, it is very key to use graphs to illustrate movement. For example, if a car is traveling along a straight road and the car's distance from the initial position is measured every second, we would see that there are many ways in which the car can move. If we were to compare the car's distance from its time traveled, creating a distance-time graph, we can notice 4 important concepts. Firstly, if the line is horizontal at a specific distance, then the car keeps the same distance over time. This means that the car is either not moving or has stopped. Secondly, a diagonal line, starting from 0, illustrates that the car is moving through time over a specific distance. What we realize is that the gradient of this graph, which is the line's vertical rise divided by its horizontal scale, is distance over time, which is the formula for speed using the DST triangle. Therefore, to find the average speed of the distance-time graph, we need to find the gradient of the line made. In this case, the gradient is constantly rising, so similarly, speed is also constant. Thirdly, from this understanding, we can denote that the steeper the slope of the line, the greater the speed, and the opposite is true for gently sloping lines. Fourthly, a graph with a curved line, starting at 0, illustrates that the line has a changing gradient, and consequently, a changing speed over time. As we already know, this is the exact formula for acceleration, and therefore shows that the car is accelerating. If the line were descending like this, then there is a negative change in gradient over time, meaning that the car is decelerating. Another graph which is important to understand is the speed-time graph, which instead of distance, illustrates a body's speed. For the same example of the car, we could distinguish three key ideas. Firstly, if the line is horizontal at a specific speed, then the speed stays constant over time, and therefore this is the average speed. Secondly, if the line is diagonal, starting at 0, then the gradient illustrates a changing speed over time, which is a steady acceleration. If the line moves like this, then the car is decelerating. Thirdly, the steeper the gradient, the higher the acceleration, while the gentler the gradient, the lower the acceleration. Finally, as an extra, to find the distance of any line, you would need to find the area under the graph. This is because of the basic formula for speed, which applies solely for speed-time graphs. Let's say we wanted to solve these two problems. How would we achieve this? For the first graph, question 1 is asking what the body is doing between points D and E. Since it is a straight line on a distance-time graph, it is not moving or has stopped. For part B, we are looking for an acceleration, which in this case would be a changing speed over time. This would be between points A and B. Part C is asking where we find a steady speed, which is a distance over a specific period, or a constant gradient. This is between points B and C. To calculate this steady speed, we would need to use rise over run of that line, which would be 50 minus 10 over 15 minus 5, which is 40 over 10, which is 4 meters per second. For part E, the distance between points A and D is simply 60 minus 0, which is 60 meters. Finally, the average speed between points A and D is the formula of speed being equal to total distance over total time, which is 60 meters over 20 seconds, which is 3 meters per second. Notice how I stated total distance and total time between these points. For the speed-time graph, we can solve it in the same way. Part A is asking for the body's maximum speed, which is simply the highest point of the line, which is 30 meters per second. To find the acceleration during the first 10 seconds, we would just need to find the gradient, which is 30 over 10, which is equal to 3 meters per second squared. This is the same method of finding the deceleration during the last 5 seconds, which is 30 over 5, making it 6 meters per second squared. For part D, to find the distance traveled, we simply need to calculate the area under the graph, which in this case, phi, is the area of a triangle, making the answer 150 meters. This is the same case for the next question, which asks us to find the total distance. Since the whole shape is a trapezium, we can use this formula to find the total distance. Therefore, putting every value, we get an answer of 525 meters. For part F, the total time is the furthest time on the graph, which is 25 seconds. Finally, the average speed, using the DST triangle, is the total distance over the total time taken, which is equal to 21 meters per second.